This week we are going to be looking at thermodynamic systems. And thermodynamics is the study of heat flow in and out of systems due to physical or chemical changes. The first of the three types of thermodynamic analyses that we're going to get into is the change in enthalpy, aka delta H. Don't forget, delta means change in something. The change in enthalpy is where we see some physical and chemical change in the internal energy of a system due to heat flow into the system, which we would call an endothermic change, or out of the system, which would be exothermic change. And we are making an assumption due to the laws of thermodynamics that energy will spontaneously flow from wherever the energy has a high concentration to low. It doesn't matter whether it's a physical or chemical changed system, and it doesn't matter what the system or the surroundings are in the universe. It's entirely arbitrary in this particular case. We'll be looking at two other ways of analyzing thermodynamic systems in upcoming videos, which are changes in entropy and changes in Gibbs energy. But we first want to start off with the change in enthalpy, which is probably the first of the three historically that scientists were able to get an intuitive and a quantitative understanding of. So we're going to look at one of the most studied of all thermodynamic systems, which is the classic cup of coffee in your room. So let's assume we're at around 25 degrees Celsius, the standard temperature recognized in science, at least on planet Earth and everyday life. That's around 298 K. So let's say that we are in a situation where we have coffee that has cooled to where it has no net gradient of thermal energy between itself and the surroundings. We could have a top on this cup of coffee, or it could be wide open. But the point is that there is no net exchange of energy because we're sort of at equilibrium here. So we're going to heat the coffee up. This is a physical change. We're not going to be breaking any chemical bonds. That would be breaking intramolecular forces. However, if we warm it up, we are going to be increasing molecular motion of the water in that coffee, and that will begin to weaken the intermolecular bonds between molecules. Unless it reaches 100 degrees, it's not enough to turn it into a gas, but it is still making those molecules more active, changing the vapor pressure and all that. So this is going to be endothermic. We're going to be having heat flowing from the surroundings of a stove, a hot plate, microwave, into the cup of coffee as the system. And so relative to the system, this is non-spontaneous. We had to push heat energy in. Which of course means taking energy out of the surroundings. You've increased your electric bill if you've done this on a stove. That was an energy investment. You put it in the microwave, it's a similar thing. Or if somehow the room gets way hotter, which we wouldn't want to be in that room, of course, then that heat energy would flow from the room, but it still is the energy lost of the surroundings to the system. So relative to the system, this is endothermic. And quantitative analysis of thousands of experiments have shown that it takes about 4.18 joules of energy per gram of water, which is what coffee 99% plus is, to get a positive change in temperature of that system per degree in Celsius or Kelvin, either way. And so this is a positive change in enthalpy relative to the cup of coffee. This would be negative to the surroundings of the coffee. If we're looking at the vantage point of the coffee, this is endothermic and it's a positive change in enthalpy. However, when the cup starts cooling down on its journey to equalizing with the temperature of the room, this is a negative change in enthalpy. We are having energy leave the system at the same rate that it enters. So specific heats are the same whether the energy is flowing in or the energy is flowing out. So the standard of specific heats of steel will be the same going in or out, water going in or out, and so forth. That's standard. You're just simply changing positive or negative. We have, in this case, an exothermic flow of heat from the system to the surroundings. And this is spontaneous because the laws of conservation of energy thermodynamics tell us that heat will always spontaneously flow from high to low. Now, how quickly that is, it doesn't matter. That depends on how effective the insulator is. But spontaneity has nothing to do with the speed of the flow. It just simply deals with, will it go on its own? Okay? Some spontaneous reactions take days, weeks, years, or centuries, and others happen in just a few seconds. But spontaneity, once again, this type of analysis does not address speed. That's a rate of reaction stuff. That's for a later time. And also we want to say is that the water will start having a decreased molecular motion, and that the intermolecular bonds will strengthen. So it's not going to be cold enough at 25 degrees to change it into a block of ice, but if we chilled it, put it in the refrigerator, we would eventually have such a strengthening of intermolecular bonds. Yes, it would turn into a solid. So a state of matter is very tightly related to the amount of strength of intermolecular bonds. We'll be addressing this a lot later. I just wanted to get that in there. But basically, to wrap things up on what enthalpy, change in enthalpy is, it is the physical or chemical change of the internal energy of all those molecules in a system due to an endothermic heat flow into the system, into the cup of coffee, or exothermic out of the system, out of the cup of coffee to the surroundings. Going in would be a positive change in enthalpy at this rate per mass unit per degree Celsius. This would be the same amount being lost in a negative change in enthalpy.